Hello, my name is 𝒂𝗄𝗄 and I'm from Team God Pace and I'm participating in CoSpace of the Singapore Open 2022. Before we get on to the more interesting bits, here's a brief introduction of myself. My team is comprised of just me, 𝒂𝗄𝗄, and this is my first year participating in CoSpace. Last year I was part of the rescue category. For the prelims, to summarize the mission in one short sentence, the mission is to obtain the highest score possible by collecting and depositing objects. The board has a few key functionalities. To save time, the board needs to avoid running out of the map, which means the boundaries, and it also needs to avoid being stuck in walls. To minimize point loss, it needs to navigate past traps to not lose its items, and it also needs to be able to navigate to and pick up super objects. It also needs to be able to identify the closest deposit zone and deposit it at that time, i.e. when the loaded objects is maxed out at 6. So here's what the prelim map looks like. As you can see, it's relatively open with very few objects in the way. It also features deposit zones that are in the corners of the field. This poses some unique difficulties, which I will elaborate on later. For the board's movement, we decided to go with differential steering, which factors in both speed and steering rate when it comes to calculating the speed at which each of the board's wheels, left and right, will turn. This allows the board to execute turns depending on various factors, which we'll go into later. So in its default state, the board will constantly take in ultrasound readings on its front, left and right ultrasound sensors. The closer they are to 0, the sharper the board will turn, as it's way closer to the wall. This allows the board to make gradual and gentle turns instead of doing a sharp turn when it's nearly flush against the wall. This saves time and minimizes time wastage from the board being stuck. As mentioned in the map analysis earlier, the prelim map featured no borders, which means that we would also have to factor in some additional considerations with regards to the board's movement around the map, so as to avoid the board moving out of the boundary and costing us valuable time in many time penalties. So throughout the game, we will calculate the distance between the front of the board and the nearest borders, which can be determined based on its compass. So, as you can see on the diagram in the slide, this is a representation of the board's compass from 0 to 360 degrees. At any point, the board can run into any two adjacent borders. So for example, if the board's compass reads 45, the board may run into the top border or the left border. We can calculate the distance between the front of the board and the two borders via Pythagoras' theorem, and we can use the minimum between these two values and US front. Basically, we will factor the minimum value into our code, and the board will operate as though the boundary is an actual wall. Additionally, in many cases, we will also need to direct the board to a certain point in the map. Certain cases where this would be necessary would be, for example, navigating to a deposit zone when the board is maxed out on loaded objects, which means that it has 6 loaded objects and it can't obtain more. This will also be useful when we are trying to navigate to a super object. Lastly, we could also use this to navigate to a zone that has more objects of a certain type to get set bonuses. This can be achieved by finding the angle the board needs to turn so that it can travel to a given point in a straight line, using trigonometry. We could factor this angle into our steering function by using this value as our steering rate. Next, this is how the board identified objects using its color sensor. Before the match, we obtain the various RGB values of the various elements on the map. This includes stuff like the yellow of the trap borders to the orange of the deposit zones, and the red, cyan, and black objects that we will need to collect for points. Throughout the game, the board is constantly comparing the RGB values from its color sensors to these sets of RGB values. A value, error, is obtained from the sum of the squared differences between a sensed R, G, B, and the values from the sets of RGB. And the whole thing is square rooted. This error is a representation of how similar the sensor's sensed color is to a given object. During a game, when either of the board's color sensors senses a color that is within a reasonable range of the target RGB values, it will stop and execute the pickup function. Lastly, the bot would also need to be able to identify super objects. Instead of obtaining the RGB values of a super object, you can make use of the simulator's function of providing the super object's coordinates after it spawns. The code saves these coordinates in variables. Once it is generated, if the bot has enough inventory space to pick up more objects, it will make its way to the coordinates and execute the pickup function when its coordinates match the coordinates that are saved. Moving on to how my bot behaves in game. As I did not capture any of my runs in the prelims, here's just something I recorded for this presentation. I'll be taking you through one full cycle of collecting and depositing objects. As the bot navigates around the map, we see its wall avoidance code in action as it avoids the boundary. It also steers way clear of the walls in the top right deposit order as well. It is also able to turn around to avoid going into the traps and losing its objects. This code is only active when the bot actually has little objects. Otherwise, it will ignore the trap, as it makes no sense to navigate around the trap when you can just zoom past it. We see the bot getting stuck in a swampland here. This is actually really unoptimal, and I would have improved further on this iteration of the code to avoid the swamps. And basically, while the bot collects objects, you can see the bot moving backwards for a few seconds. This is actually a workaround that I came up with, as a solution to the wacky placement of the deposit zones, as it was rather hard to guarantee that the bot will be able to move out of the deposit zones after staying there for 3 seconds and having the appropriate LED light on, as it's in the corner, and it might go out of the boundary, resulting in an unsuccessful deposit attempt. So this gives it enough time to move out of the deposit zone so that the objects are actually deposited successfully, as you will see soon. So now that the bot has 6 objects, it will start navigating towards the deposit zone. You will see that the bot is able to steer clear of objects and also traps in the way, as both of its sensors senses the orange of the deposit zone. It will deposit, and you see it moving backwards now. And that's a successful deposit. Although CoSpace may seem pretty far removed from the real world, we can actually apply some of the knowledge that I've gained to the real world. There are actually examples of search and rescue robots that are already present and used in our daily lives. One example would be RoboCule. RoboCule is a rescue robot from the Tokyo Fire Department, and it's designed to locate and safely retrieve victims from disaster sites. It uses ultrasonic sensors and infrared cameras to locate trapped humans, and gently loads the injured person into a cart to be transported to safety. It even has an onboard oxygen canister. Already, we can see some similarities between the functionalities of the real-life robots to the robots that we have programmed in CoSpace. We can expand on these real-life inventions by applying concepts from CoSpace. One example would be better targeting. In CoSpace, one can set the robot to target differently colored objects for set bonuses to attain the most points possible. Depending on the time conditions, one can also set the bot to collect the objects that are closest to it first, if it does not have enough time to complete a deposit. This object pickup strategy can be used for these real-life robots, to rescue victims that are in dire need of medical assistance first, or to rescue victims that are closest to it and it is impossible for the rescue robot to get to further victims. This maximizes the number of lives saved. With that, I've come to the end of my presentation. Thank you so much for your time.